Hi, I'm John Ainsley from Doulos. I'm going to describe some of the key concepts of the easier UVM code generator. I'm going to tell you a few things that it's good to know before you start running the code generator. Let's start by talking about inputs and outputs. The code generator itself consists of just one Perl script. It takes a set of input files and generates some output files. On the input side, the main files are a set of interface template files and a common template file. There's one interface template file for each interface on the DUT, which will be driven by an agent in the generated UVM environment. There's also a common template file, and that contains both settings that are common across all the interfaces and also settings for the top-level env, the test, and the modules. As well as the template files, there's a pin list file. The pin list file contains the mappings that are used for generating the DUT instantiation, that is, mapping the signals and variables within the interfaces to the pins on the DUT. Then comes the DUT directory. The DUT directory contains all or many of the files that constitute the DUT, and the code generator finds the DUT files using a single file named files.f, which must be located within the DUT directory. This is a file containing command line flags that are used by the simulator. Then comes an include directory, and below that directory are any user-defined code fragments that you want to see generated within the automatically generated code. I'll say a lot more about that later on. So the code generator takes this set of input files and generates a set of output files, all within a single directory. The actual directory name defaults to generated TB, but like most things in the code generator, it's customizable, so you can actually change this name generated TB from a setting in the common template file if you really want to. Within this output file directory, there's a complete copy of the input DUT directory, so the code generator just copies over the files one for one from the DUT directory into the DUT directory within the generated files. There's another directory that contains a set of automatically generated simulation scripts. There are simulation scripts generated for each of the main system Verilog simulators. Having run the code generator, you can just run your chosen simulation script and it will compile and simulate all of the generated code out of the box, which is very handy. Then comes the TB directory. The TB directory contains all of the generated test bench or verification environment code. That is the automatically generated agents, which were driven and controlled from information within the interface template files. The top level env and the top test, they were controlled by the common template file. And also a complete copy of the include directory, that is any user-defined fragments that are inserted into the generated code. So there's a very clear relationship here. You start off with a set of input files, run the code generator, and it generates a set of output files, overwriting any files that were already present in those output directories. As an option, you can have the code generator create a backup of the output directories, just in case you wanted to avoid overwriting the existing files for some reason. But typically overwriting the existing files is not going to be a problem because you're going to go to great pains to make sure that you don't make any changes to the output files that you couldn't reproduce. Of course, that's always one of the issues with code generators. What do you do if you change the generated code? And the answer in the case of the easier UVM code generator is that you try not to change the generated code. What you try to do is to set up everything that you're going to need in advance within this set of input files. If you really do need to change the generated code for some reason, then the best way to do that is by running a script immediately after you run the code generator script. So use the code generator script to create a new pristine set of output files, and then immediately run another script that makes any changes needed to those files, if that's really what you want to do. Anyway, there are other alternatives, as we'll see. Most of the time, the output files are going to be self-contained. That's why the code generator script copies over all the DUT files and the include files into this output file set. You can take that output file set and use it as your master file set for your project. Most of the time, the output files are self-contained, The one exception is if there are any external references within the input file set. So if within System Verilog files in the .dot directory or the include directory, you have any include directives or you import any System Verilog packages, then those include directives and imports will just be copied one for one into the output file set. In other words, the output file set can still make references to external files. Looking at it another way, include directives and import declarations are regarded as being opaque by the code generator. The code generator doesn't understand them. It just copies them over verbatim into the output file set. So if your .dot directory actually contains files that reference other external files, exactly the same external file references will sit in the generated files, and in that sense and that sense alone, the generated file set might not be standalone. One example of that is the include directive that includes the UVM macros and the import declaration that imports the UVM package. Those directives and import statements will just exist in the output file set. In other words, the output file set won't include the UVM base class library itself. Each interface template file defines one agent and also defines how that one agent is going to be instantiated. The interface template file results in the generation of one type set, where a type set literally means an interface and a set of types. Actually, these types are all System Verilog classes, and all of the System Verilog classes are contained within a single package. So for each interface template file, you'll get one interface and one package that contains all of the classes shown here, and maybe some others, depending on the exact settings that you set up in the interface template file. So here you have an agent, its sequencer, driver, monitor, sequences that run on the agent, transactions, configuration classes, and so on. But the interface template file also defines how that agent will be instantiated, so in this case within its own env. And there's a few choices here. It's very important that you understand those choices. It's also very important that you get this concept that for each interface template file you have one type set. Because each of these are literally System Verilog types, if you make multiple instances of any of these types, all of those instances are going to be symmetrical. They're all going to be objects of the very same System Verilog type. Similarly, if you have multiple instances of this interface, you're making multiple instances of one and the same System Verilog interface. We'll talk a lot more about the consequences of that in a minute. Anyway, there's a couple of choices to how you instantiate an agent. Let's look at that next. So the first way to instantiate an agent from the code generator is to have it instantiated below the top level env. That's what happens by default, or you can force it by setting agent has env equals no in the interface template file. So in this case, agent A and agent B are both instantiated with agent has env equals no. They're both instantiated along with their coverage collection components within the top level env. The second choice is to set agent has env equals yes, and you can mix and match. So in this second example in the middle column here, agent A is instantiated within its own env. We've got agent has env equals yes. Agent B has agent has env equals no, so agent B is instantiated directly below the top level env. So the code generator can generate code that has a test which instantiates a top level env, and that top level env either directly instantiates agents or instantiates lower level envs that are specific to the individual agents, and you can mix and match. The third choice is to have an agent instantiated within the env of another agent. So over on the right here, agent A has agent has env set to yes. Agent A is instantiated within its own env, within the top level env. And the interface template file for agent A has a setting that says additional agent equals B. And so agent B is instantiated within the env of agent A. You can set as many additional agents as you like within an interface template file, and that means you end up with a whole collection of agents all within the same env within the top level env. So there we are, there's a few choices. So I've been talking here about settings that you can put within an interface template file that control how that agent gets instantiated. Let's look at a couple more of those settings. One that you might want to know about is number of instances. By default, the number of instances of an agent is 1, but if you set number of instances to a value greater than 1, then you get multiple instances of that agent. So in this case, agent A is instantiated within its own env, but we've got 2 instances of agent A set in the interface template file, and so we get 2 symmetrical instances of the same agent and 2 symmetrical instances of the coverage component associated with that agent. And when I say symmetrical instances, I simply mean we've got 2 system Verilog objects here of the same type. So to all intents and purposes, they're going to be the same. Of course, they'll have different values dynamically during simulation. They'll be different objects, different agents, but their properties are all going to be the same. Another instance-specific setting is agent is active. So within an interface template file, you can control whether that agent is going to be instantiated within active mode or passive mode. So with agent is active equals UVM active, the agent will have a sequencer driver and monitor. With agent is active set to UVM passive, it'll just have a monitor. The way that this is implemented is that these settings get put in the top level configuration object. And from there, the information percolates down into the configuration object for the agent. That gets read by the build phase and connect phase code of the agent, which decides whether or not to instantiate sequencer driver and whether or not to connect them up. One of the most powerful aspects of the easier UVM code generator is that you can insert user-defined code fragments within the automatically generated code. That's the thing that makes the code generator useful deep into a project, because you can continue to run the code generator again and again to automatically generate the boilerplate code and so reflect any changes that you've made in the automatically generated code. But at the same time, have your own code inserted and reproduced within that automatically generated code. So to do that, you put settings into the template files. So here we have an example within the common template file, and the setting in question is top-env inc after class. In other words, we're sucking in a user-defined code fragment from the file file.sv within the include directory on the input side, and we're having that code included within the automatically generated code on the output side. And you've got 2 choices. Either you can have the code generator generate a system Verilog include directive, or, as we've shown here, you can use the inline flag on the setting, and then the code generator will inline the code fragment within the automatically generated code. So in other words, the setting within the common template file sends the code generator off to suck in this file, file.sv, and with inline against this setting, the code generator is going to take the contents of this file line by line and copy them into the automatically generated code. The code generator puts in a comment here to actually tell you what it's done and tell you the name of the file that it's sucked in. So in this particular case, what we're doing is sucking in some methods after the end class line of the top-level environment class. If we're going to start bringing in our own user-defined code, there comes a point where you might actually want to start overriding or replacing the automatically generated code. So when you reach that point, you can selectively have the code generator not generate code itself. And there are settings in the template files to do that. So here we've set top-env generate methods after class equals no in order to suppress the generation of the build phase, connect phase and run phase method definitions after the class, and then we replace those entirely with user-defined method definitions from our user-defined code fragments. The code generator supports a large number of settings for both suppressing automatically generated code. Those are settings with names such as generate methods inside or generate methods after. All of these settings will be set to yes by default, but you can set them to no in the template files in order to suppress the automatic generation of the code. And then there's a range of settings for inserting your own code into the automatically generated code. This isn't a comprehensive list of settings by any means, these are just of commoner examples. So for each class or module, there are settings such as ink before, ink inside and ink after to have your own code inserted before, inside or after the construct. And then there's some more specialised settings as well. So for particular classes, you might be able to set to have code prepended at the front of the build phase method, at the back after the build phase method, or after the connect phase method, just to show you some of the commoner examples. And you can see it from this diagram here that you can control and have your own code inserted pretty much anywhere within the automatically generated code. Now let's talk about differentiating multiple instances. And this is conceptually pretty important. So what happens, as I've said already, is that each interface template file results in the generation of one typeset, which literally means an interface and a set of classes within a package. If we want to have multiple instances of the same interface or the same agent, then you've got a couple of choices. If you want multiple instances of the same agent and you want those instances to be symmetrical, if you want them all to look and behave the same, then you can use the number of instances setting within the interface template file. So here we have an interface template file with number of instances equals 2. When we run the code generator, we'll get one typeset. And that typeset will include within it all the code that we've sucked in from the include files. That is, this typeset might be highly customized with a whole bunch of user-defined code fragments. Nonetheless, every instance that we then make of this typeset will be identical. So although you can highly customize the generated code, if you then end up with two instances of the same class or two instances of the same System Verilog interface, you're going to have two instances of an identical class or interface, of course. That then raises the challenge of how you differentiate between the structure or the behaviour of this code in your complete verification environment. And what I'm talking about here is making the code look and behave differently. Of course, if you've got two instances of the same object, those two instances of the same object can have different values at runtime, but the behaviour is going to be the same unless you do something pretty smart about it. So there's two cases to consider: the components and the things that aren't components, which means sequence items. So in the case of UVM components, we can always differentiate the behaviour and structure at runtime by setting factory instance overrides. So within your UVM test or your top-level UVM env, you can set a UVM factory instance override controlled by the template files, and then have that replace one instance by another to customise its behaviour. That's in the case of components. In the case of transactions and sequences, you haven't got that luxury even if you want it, because you can't use UVM factory instance overrides on sequences and transactions because they're not components. You can set factory type overrides, and Easier UVM makes it extremely easy to do that. There's settings in the interface template files to do exactly that, to generate factory type overrides, but then those factory type overrides are going to override your transaction types and sequence types and virtual sequence types for all instances of this type set. If you actually want different instances of the same class to have different behaviours, you can do that, and the way that you would do that is to differentiate the settings in the top-level configuration object. So, flipping back a slide, you would use settings within your common template file in order to change the contents of the top-level configuration object. The instance-specific settings within the top-level configuration object would then percolate down through the hierarchy here so that each agent config has different settings, and the sequences running on the agents can then pull out instance-specific information from the agent configs, and thus have different sequences on different instances of the same agent behave differently. So that is possible. But the guideline here is if you want multiple instances of the same interface and the same agent that are by and large symmetrical, then the way to achieve that is to use the number of instances setting in the interface template file. On the other hand, if you want multiple instances of the same agent and you want them to be significantly different from each other, then the best way to do that is to use a different interface template file for each agent, even if it's nominally the same agent. So that could be, for example, because you've got multiple instances of the same agent and you want to run very different sequences on those multiple instances of the same agent. Or another reason might be if you've got multiple instances of the same agent, but they're actually being used to drive very different interfaces of the design under test. For example, to use a trivial example, you might have an APB agent within one interface and another APB agent within a completely different interface. So if you've got the same agent interfaced in different contexts, then you would give each agent its own interface template file, and it can then have different include files, and you're going to generate distinct typesets for each agent so they can behave as you please. So now you know the key concepts, you can start running the Easier UVM code generator for yourself. You can get access to the Easier UVM coding guidelines and the code generator from the URL shown here, and you're going to be downloading the code generator under an Apache 2.0 license, so the source code is yours to do whatever you like with. So at Doulos, we're giving you all of this free stuff because we'd love to see you on one of our training classes. At Doulos, we deliver training worldwide in the topics of hardware design and verification, embedded systems and ARM processor technology, FPGAs, and also ESL and SystemC. So if you're interested in training in any of these topics, check out doulos.com.